This is how my garage looks like. This is how the operating looks like where I'm working most of the time. And occasionally I have one of these on an anesthesia machine as well. You will see that there are very little references because there are very few studies that give extensive comparisons on CO2 absorbers in vitro settings that resemble what we do in real life. So today I'm going to present results of measurements I did over the last 3 years over more than 200 canisters. I'm going to go over the first part pretty fast. This is a flash refresher course of last year, and I'm going to move on. Then I'm going to go a little bit slower. Just a reminder, 1% CO2 is 1% of 760 millimeters of mercury. So some anesthesiologists use the percentage display on their screen if they look at the capnogram. Others use millimeters of mercury. Why do we need CO2 absorbers? Here is our circle breathing system, the fresh gas flow, inspiratory limb, the lungs, expiratory limb, and the ventilator. As long as the fresh gas flow is higher than the minute ventilation, the bellows will fill with fresh gas flow only, and the composition here inspired will match the delivered. However, once we are starting to use lower fresh gas flow, exhaled gas will be used to fill the bellows. It will be re-inhaled together with the fresh gas during the next inspiration. We want to get rid of the CO2, so we need CO2 absorbers. If we do not place a CO2 absorber in an adult undergoing a laparoscopy who is exhaling 160 milliliters CO2 per minute in a circle breathing system, nothing will happen as long as the fresh gas flow is higher than the 5-liter minute ventilation. If we decrease the fresh gas flow to 0.3 liters per minute, the FI CO2 under these conditions will become 33% or 253 millimeters of mercury, which I think is lethal. When to replace the canister, this is your typical capnogram, this is your Untitled Alveolar CO2, and this is your inspired CO2. Normally, this goes back to baseline 0. At some point, you may see that the inspired CO2 increases, and that denotes that the canister is starting to exhaust. I do not care too much about the inspired CO2, because what's really important is the Untitled CO2. That's what's important to my patient, because it reflects the arterial CO2. So the question then really becomes, what's the effect of the inspired CO2 on the Untitled CO2? If you do the mass balances of CO2 going in and out of the lung, this is the formula you end up with. It's called the Alveolar Air Equation. And the only thing I would like to say about it, that the effect of the inspired CO2 is more or less additive on the Untitled. So, clinically to me, that means that I don't care that the FiCO2 rises, as long as the effect of the FiCO2 on the Untitled CO2 is not important for my patients. A normal Untitled CO2 is around 35 millimeters of mercury. If it rises by 4 millimeters of mercury, which is 0.5%, I think that for most patients is not a problem. So that, I think, is one of the reasons why in most studies 0.5% is used as the cutoff value to replace the canister. Okay, NAVAt 2014. So I'm going to present the results of more than 200 measurements over the last 2 to 3 years. I'm going to start by making sense out of these pre-packs. I want to mention that I only tested pre-packed canisters. The reason being that I have an interest in automated low-flow anesthesia. Pre-packs there are very convenient. They keep the volume small. You don't have it's easy. You don't have leaks when you replace them. So I'm only going to talk now about pre-packs. And in the first part, or the major part of the lecture, I'm going to talk about pre-packs that you can use on an ACES anesthesia machine, simply because that's the machine I arbitrarily started to measure canisters with but I'll show you some data with other machines as well. The key to rationalize the plethora of canisters is to understand its composition. And there's two broad categories. One is the calcium hydroxide-based canisters, the granules we're most familiar with, and the lithium hydroxide product. And this is going to be available in Europe soon. These are the granules we're familiar with. This is basically a sheet wrapped around a core through which the CO2 passes. It's called the spiralite. All the other canisters that we have available are calcium hydroxide-based canisters. It does make sense to further subdivide calcium hydroxide-based canisters according to their sodium hydroxide content, more than 2.5, less than 2.5% on a weight basis, or none. Why? Well, I want to note that as long as there's at least a little sodium hydroxide, there may be a little production of compound A and carbon monoxide with these canisters due to the interaction with sevoflurane and desflurane, the clinical relevance of which, however, is questionable. I want to point out something here. You see lithium hydroxide here and lithium hydroxide here. These are apples and oranges. You can't compare them. The lithium hydroxide here in the litho-lime product is actually a replacement for the sodium hydroxide, and it accelerates, it's a catalyst, it accelerates the interaction between CO2 and the calcium hydroxide. In this product, the lithium hydroxide is the primary CO2 absorbent, the spiralite. So two different animals altogether. Now, how to study canister life? Well, this is the experimental setup I've been using over the last few years. And again, we have our circular breathing system, and I'm feeding 160 milliliters of CO2 into the tip of this balloon that is simulating the lungs, a 2-liter bag. And I am ventilating this bag with a 5 liter per minute ventilation. Then I pick my choice. I'm going to select the brand, for example, Medisorb. I take 12 Medisorb canisters, and I'm going to place them in the circular breathing system. I take my first canister, I choose a certain fresh gas flow, I let it run, and I look at how long it'll last. And I'll do that with 12 different fresh gas flows, and after that I'll repeat it with a different brand. So, Medisorb, 12 canisters, I test one with 0.25 liters per minute, one with 0.3, 3.35, etc., up to 4 liters per minute. So I finish this one, I take a new canister, the second one, I go to the other fresh gas flow, and I test 12 canisters with different fresh gas flows in this setup. You may expect, of course, that the lower the fresh gas flow is, the more breathing there will be, and the shorter the canister life will be. How to quantify canister life? Well, let's say we're going to start with the first brand. I mean, Medisorb, whatever. And I'm going to take the first out of these 12 canisters. And I'm going to put it in the circular breathing system and use a fresh gas flow of 0.2 liters per minute. And over a long time here, nothing will happen because the CO2 absorber will be absorbing the CO2. At some point, the CO2, the inspired CO2, will start to rise. And this is the typical exhaustion pattern. How are we going to quantify this? Well, let's measure the time to the different FiCO2 thresholds. For example, it takes 8 hours to get to an FiCO2 of 1%, 0.2%, sorry, 0.2%, 0.3%, 0.4%. It takes 11 hours to get to 0.5%, and so on. And it takes, for example, this is just a theoretical example, it takes 12 hours to get to an FiCO2 of 1%. And then we stop. I mean, I stopped measuring the canisters once the FiCO2 had reached 1%. Now let's display these results in a different way so we can assess the effect of fresh gas flow, calculate costs, and compare different brands. And what I'd like to use for that is what I call the fractional canister usage. This is key to understanding the rest of the lecture, so I'm going to explain it in a few slides. As I mentioned, with the 0.2 liters per minute fresh gas flow, it took 8 hours, 11 hours, 12 hours to get the FiCO2 to rise to 0.1, 0.5, and 1%. Again, if you read this, it means if you decide to replace the canister, once you see 0.1% on your capnogram, you will have worked 8 hours with one canister for that particular fresh gas flow. In other words, you will have used 1/8 of that canister with that fresh gas flow if you would be replacing him once you see 0.1%. So now the conversion to FCU, the fraction of the canister you use per hour. If I use 1/8 of the canister per hour, I'm using 0.125, a fraction, or in percentages expressed, 12.5% of the canister per hour. And again, I call this the FCU. It can be expressed as a fraction or as a percentage of the canister used per hour. So, you have it right. So one more time, if you see FCU for 0.1% is this number, it means if I place the canister when the FiCO2 is 0.1%, I will have used 0.125 or 12.5% or 1/8 of the canister per hour. If you want to convert it back in hours, you just have to divide 1 by the FCU. Now let's do a little hocus pocus here. So this is the first canister out of the 12-1 of the first brand. I'm going to plot these results in a plot where I have the fresh gas flow that I used for that particular canister and the FCU, the fractional canister usage, for the different FiCO2 thresholds. So again, my first canister, which I used with a fresh gas flow of 0.2 liters per minute, that's how long it takes to get to the respective thresholds. So here are these data again. 8 hours to get to 0.1%. So 8 hours to get to 1% means that I used 1/8 of the canister, 12.5. The fresh gas flow was 0.2 liters per minute. Here is the 12.5. It took 11 hours to get to 0.5%, which is an FCU of 9.1. 100 divided by 11 is 9.1. I place it here. The fresh gas flow I was using during the experiment was 0.2. And the same thing for the 1% threshold. That's what we get. I take my second canister. Now, again, same brand. And I'm going to use a higher fresh gas flow. Obviously, it will take longer for the FiCO2 to rise. Let's say, for example, it takes 17, 23.5, and 26.5 hours to get to these respective thresholds. Again, it lasts 17 hours to get to 0.1%, I used 100 divided by 17 is 5.8% of the canister per hour with a 3 liter per minute fresh gas flow. And the same thing here for the other thresholds. And I'm going to study more and more and more fresh gas flows. And what I get ultimately is a graph like this. Here's your fresh gas flow, and here is the fractional canister usage for the different FiCO2 thresholds. I want you to note that this line here intersects at 5 liters per minute. Why is that? Because, remember, minute ventilation was 5 liters per minute. If the fresh gas flow is higher than 5 liters per minute, there is no rebreathing and nothing will be used. The canister will not be used. Everybody okay? Bit warm maybe? Okay. So these are the results of my measurements with the ACES. Again, this is an example. I'll show you the actual results in a moment. Now, as it happens to be with the ACES, there is a linear relationship between the fresh gas flow and the FCU for the different FiCO2 thresholds. That's actually convenient because I can just do a linear fit. And I think we all remember this from, I think, elementary school. That is the equation of a straight line. So I can say that the fractional canister usage, the percentage of the canister used per hour, equals the slope of this curve times the fresh gas flow plus the intercept. So if I know the slope and the intercept for the different FiCO2 thresholds, I can define each of these lines. And that's what I've been doing over a long time. I determined those parameters for all the prepacks that I had available for the ACES. For all the FiCO2 thresholds, ranging from 0.1 to 1, and for each different brand. So that actually took a lot of time. I mean, if you use a fresh gas flow of 4 liters per minute, it almost takes a week to let it run before it exhausts. So many, many brands, 12 canisters of each with a different fresh gas flow, and I want to point out that they were all the same lot number. Here are the results. If all is well, you should have gotten this in the handout, and it's going to show you the graphs and tables that I will go over pretty quickly, so you can interpret the results yourself. I have no conflicts of interest whatsoever. I want to say this again. So here you can see the FCU fresh gas flow plot, and this is when you decide to replace your canister once you see some FiCO2. And these are the results. So this one here is the most efficient one, and as you go up, you have the less efficient canister. Obviously, if you let the FiCO2 rise a little bit higher, to 0.5%, then you will see, here is 20, here is 10, you will use less of the canister per hour, and you will also note that the relative position of the curves to one another shifts. I'll explain that to you in a moment. So these are the numbers you need to do the calculations yourself. They're in the handout. You're welcome to have them. You have the slopes and the y-intercept. If you want to calculate how much you use, please go ahead. It's all in the handout. If you can mail me if you have any questions on how to do it. Now, the y-intercept and the slope allow comparison of the canister performance of the different brands. It's a straight line. If I just take the ratio of the parameters of the line, I can determine the relative efficiency of the different canisters. If you want to calculate the cost of a canister per hour, you just take the FCU for a particular threshold and a certain fresh gas flow, and you multiply it by the cost of one canister, expressed as a fraction, and then you know how much the canister will cost you per hour, again, for a CO2 production of 160 milliliters per minute with a minute ventilation of 5 liters per minute. So, I actually calculated the ratios here for you of the parameters of the curve. It's in the handout. And what I did here, I arbitrarily assigned the number 100 to the most efficient canister, which is here. And then I just took the ratio of the parameters of the y-intercept or the slope, because it's a straight line. It doesn't really matter. Because it's a straight line that goes to 5 liters per minute, it doesn't really matter which of the two parameters you use. And I think these graphs kind of speak for themselves. I'm not going to do any interpretation about this. So this tells you how much more you need relative to the most efficient one: Amsorb, Lovelsorb, Metasorb EF, Metasorb, Spherosorb, Little Lime, Spiralit, for the different FiCO2 thresholds. Another way to express the results is like this. What is the relative efficiency relative to the most efficient one? And again, you can see these calculations here. Again, I want to point out that this was just one lot per brand, but this is a lot of canisters, 12 times all these canisters. I tested one lot. This obviously, when I did the measurements with the different fresh gas flows, all the canisters were from the same lot. I wanted to test inter-lot variability, so here I went again. I took 2 different boxes with 6 canisters of the different brands, and I used a 350 milliliters fresh gas flow. So took my circuit again, canister goes in, 350 milliliters fresh gas flow, 6 canisters of one lot, 6 canisters of another lot. And here's what I get. Here's the FCU, the fractional canister for lot 1 and lot 2. Metasorb EF, Amsorb, Lovelsorb, Metasorb, Spherosorb, Little Lime, Spiralit. There were some differences for, these are the differences, and some of these were statistically significant. That doesn't therefore immediately translate into clinical difference. We'll talk about that in a moment. And in some canisters, the variability expressed as the coefficient of variation was more pronounced than with the others. I'll show that to you in another graph where it's more clear. I think these are the most complete results I have so far, because these are the combined results of two different lots. I'm happy to test a third lot and a fourth lot. Again, here I'm organizing them according to how much more you need, but this, relative to this one here. The relative efficiency, how much more you need, expressed as percentage, here expressed as a fraction. I also want to point out that by actually weighting, here are the different brands. This is how long the canister lasts, expressed in hours this time, how long it takes to get to 0.1% in hours. This is the average of the two lots. This is how many hours you gain by weighting 2.5%, and that's the relative gain you get by weighting until the FiCO2 is 0.5%. Again, all these data are in the handout. It will be on the website soon. This is a graph I really like. I'm presenting the same results in an entirely different manner. And let me start arbitrarily, just for purely didactical reasons. I'm going to look at this one here. This is the spirit. And here you can see the 6 canisters of one lot, the 6 canisters of the other lot, and this big figure here, this big sign, mark, is actually the average of all these. This here is the x-axis, and it displays in minutes the time until the FIC reaches 0.1%. So with the spirit here, you can see it takes 1,080 minutes with the fresh gas flow of 350 milliliters per minute under the experimental conditions defined to get to 0.1%. Now the other thing, of course, is the rate of rise of the FiCO2. And I have a different axis here. And this is the time, again in minutes, and it tells you how long it takes for the FiCO2 to go from 0.2 to 0.9%. So this tells you something about how fast do they exhaust once they start to exhaust. So for the spirit here, 1,080 minutes before it starts to exhaust, but once it starts to exhaust, you see it only takes 60 seconds or less, half an hour, for the FiCO2 to increase from 0.2 to 0.9%. Again, this is lithium hydroxide, where lithium is used as the primary absorbent. Now let's go to those canisters here, the calcium hydroxide canisters, that do contain a catalyst, either sodium hydroxide, at least 2.5 or 2.5%, or lithium hydroxide, the little m, again used here as a catalyst, not as the primary absorbent. And you can see that basically for all these brands here, all these products, but similar, that the duration here, before the FiCO2 starts to rise, is pretty similar. The rate of rise, once it starts to rise, is different between 3 products. You can see that here. For example, this one here, 720 minutes. But once it starts to exhaust, it's going to exhaust a bit faster than this one. Also look at the spread here, for example, the Medisorb canister, 6 canisters here, lot 1, 6 canisters here, the second lot. So there's actually more spread than with this product here, for example. I'm going to move on to the next one. This is the M-Sorb Plus and the low flow sorb. So this one is the calcium hydroxide without any catalyst. You can see that this one here lasts 360 minutes and this one around 540 minutes until the FiCO2 is 0.1%. However, look at what you gain if you accept a higher FiCO2 threshold. Here is when it starts to exhaust, but it takes 240 minutes for the FiCO2 to rise from 0.2 to 0.9%. So how I interpret this clinically is that it's important for these canisters to wait until the FiCO2 is at least 0.5%. And then here we have the Medisorb EF. This one is exhausted after 360 minutes, and actually once it starts to exhaust, it's actually pretty fast. But again, note how close these 6 lots are, and these 6 lots here. Not a lot of variability, though. Okay, I tested canisters, but now let's have a look at canister performance on a weight basis. Because I'm going to use the same data set, but look at the weight contained in the different canisters. This is the brand, this is the weight of active ingredient. Again, this is a lithium hydroxide based product. These are all calcium hydroxide based canisters. And you can see that there's quite a bit of difference in the weight of the actual product in the plastic container. So I'm going to express the same results now as how many minutes in the experimental conditions I outlined, how long does the product last per 100 gram of product. And then you get this graph. So here on the x-axis you see the FiCO2 threshold. When would you like to replace the canister? And this is how many minutes you get per 100 gram of product to get to one of these FiCO2s. You can see these are all the calcium hydroxide based canisters. This is the lithium hydroxide based canisters. And this is about double. It must have to do something with the molecular weight of lithium versus calcium. And so, but also look at the differences here in the calcium hydroxide absorbers themselves. If you look at the performance on a per 100 gram product weight basis, you can see here the relative differences. For the AMSOP canister, for example, it's really important you wait until they put the FiCO2 is 0.5, because you're almost double the time you get out of 100 grams of product. And I'll leave the interpretation of the results up to you. Again, they are in the handout, and I'll post them on the website. Towards my final slides, these were the results for the ACEs. All anesthesia machines differ because they have different rebreathing characteristics. So their canister usage may differ over the entire fresh gas flow range as compared to another anesthesia machine. That'll take me another half year to complete, actually. So I do expect differences with the Zeus or Zeus because there's a blower continuously blowing or circling the fresh gas flow in the breathing system. Maybe this has a cooling effect on the canister that affects canister usage. Also, I'm not sure whether the relative amount of granules contained in the different prepacks are the same. So that it is work in progress. I had hoped to present some data today, but it's just been incredibly busy. We also tested the Maquet canister. I'll give you the result in the next slide. What I mentioned though here, something peculiar. Remember when I talked about the flow eye? It starts off with a very high fresh gas flow, which exponentially decreases over 15 minutes to 0.3 liters per minute. So obviously canister usage during the first 15 minutes will not be that what it would be during the maintenance phase later with the 0.3 liter per minute fresh gas flow. So I'll give you more exact numbers later or next year when I have the different results for the different products for the different machines. I want to say be very careful to, I'm plotting these results on this graph, but remember this was all done with the ACEs. And the Maquet canister was tested with the flow eye, and if I take the FiCO2 threshold of 0.5%, it's 87 minutes, so it ends up somewhere around here. The Draegersop and Draegersop free, and around here. But more results to follow in a few months or half a year. Again, it takes quite some time to get the results. So I want to conclude. 1, the Spirit is the most efficient one, both based on a canister and a weight basis. 2, the presence of a catalyst, not one of these two, with the calcium hydroxide canisters affects duration and the rate of rise of the FiCO2. If you use a canister without a catalyst, wait at least until the FiCO2 is 0.5%. There is some interlot variability between brands. I'm willing to test more. On a weight basis and for an FiCO2 of 0.5%, differences between calcium hydroxide canisters, absorbents, seem relatively small if you compare them to the Spirit. Differences in canister life are related, at least in part, to differences in fresh granule content. And I think FCU is a convenient way to compare canisters. Again, all this information should be in handout, and I'll post them on the website later. Thank you.